Okay, I've had a couple of people come to me today asking the same question about how to extract the spanwise lift distribution out of the SwanVLM Vortex Lattice code that you've been using to do your preliminary aero design. Now, just a reminder, at the end of the program, the kind of visualization that you get back from SwanVLM looks something like this. And notice that what you have, the angle of the plot is a bit misleading. And notice that the scales also on these axes here aren't consistent. So it sometimes looks a bit funny in this plot. But I'll show you something a little bit clearer later on. And what's being plotted here is the delta P, so the difference in pressure between the top and bottom of your wing over the wing section, measured in pascals. Okay, so let's just remember that for a minute. And I'll run a very simple example quickly. So we're going to run a single wing, which is made up of a single section, using an airfoil cross section that's been taken from this file here, VR1, root chord 0.15. Section span 1.5. There's no taper in this wing, so the tip chord and the roots chord are the same, and a section sweep of 20 degrees. So that's what we're running, and I'm going to run it on a very coarse grid of, well, a total of just 10 panels per wing. Other thing to note as well that we're going to mirror this wing in the ZX plane, so you're effectively modeling both sides of the wing. So let's run that. I'm hoping this will run nice and quickly. So at the moment it's just reading in the geometry from that Excel file. In fact, I might have a problem here in that this is open. I'm just going to run that again because I should have had the Excel file closed. Because remember, it writes the results that you get back into that Excel. It adds a worksheet into that Excel file with your results. At the end of doing the analysis, it will ask you, do you want to create some nice pictures? Now this is the point at which, if you choose yes, it will create for you those images that end up in the GIF animation. So let's ignore the other outputs because that doesn't seem to be the issue at the moment. So that's what's generated this plot here, which is looking kind of at an angle down at your wing, and what's being plotted, this is the spanwise direction, this is the chordwise direction. And what's being plotted is the difference in pressure between the top and bottom surface, which of course is the thing that generates your lift. So the question that's been asked of me is, well, how do you go from that to the thing that you need to do to work out your shear force and bending moment distribution along the wing, span-wise? So I thought I'd show you how I would go about doing that, or at least point you in the right direction. So that plot is plotted in the routine, or the function that is called make pictures. And down at the bottom here, in this section here, for each wing, we're cycling through each of the panels to generate those pictures, and then eventually they're created down here using this command surf x, y, z, and then the thing that's being plotted is the C value. So what I'm going to do is just insert a breakpoint here in the program. So the first point it gets to this section of the code, it will stop, and hopefully that will allow me to demonstrate what X, Y, and C are. So let's run that again. Now this time it will stop when it gets to that point. Okay. And X, Y, and C should now exist in your workspace. So C is the thing that's being plotted, and we know that that thing that's being plotted is the pressure difference between the top and bottom surfaces. Now, this is a grid of data with a certain number of columns which run from 1 to 101, and a number of rows running from 1 to 201. And you'll notice that lots of the numbers in here are NaN, not a number. But that's because your wing sits somewhere in the middle of all of this. Okay, so the data that ends up being plotted in those pictures is contained in here. And what you'll find is that this effectively, so where the numbers exist in this matrix relate to the shape of the wing that you're studying. So this in fact is the root of the wing, and then as you go down this matrix you're moving in the spanwise direction down the wing, and as you move in that direction you're moving in the chordwise direction. So remember, we've got a 201 by 101 matrix, and within that you've got the information about the delta P's for the wing that you've analysed. Now, what's important to recognise here and pick up on is that in the X matrix, for each of the points in that C matrix, the X matrix gives you the X coordinate at that point. So again, as you can see that in this direction the X values are changing, implying that this is the chordwise direction in that matrix. And if you open the Y matrix, it's a 201 by 101 matrix, but this time the Y values are increasing in this direction, so this is the spanwise direction. And then the Z actually gives you the profile of the wing itself. But for what we're interested in doing, we don't care about what's happening in Z. All we're interested in is the X and Y coordinates, which are kind of the coordinate system if you're looking down plan-wise on your wing. And then the value of delta P, which is contained in the C matrix. So how do we go about turning the numbers in those matrices into a spanwise plot? Well, the first one I'm going to do is let's extract A and B, and I'm going to call A and B. I'm going to set A and B up as being the size of that C matrix. So we can write AB is equal to the size of C. So we've now got the number of rows in matrix C, the number of columns in matrix C, and this might be different depending on the resolution you use when you set up your problem. These numbers won't necessarily be 201 and 101, so you need to extract that. And what I'm going to do, remember that in the A direction, that's the spanwise direction, when we're going to try and work out how the lift is varying in the spanwise direction. So I'm going to initialize a matrix called lift of size A. So I'm going to create a matrix of zeros of size 201 by 1. And now what I'm going to do is, first of all, create a loop in the spanwise direction through matrix C. So I'm going to do for IY is equal from 1, goes from 1 to A, which is the number of, I'm going to bring the C matrix back up here. So I'm looping down in this direction here. So we're going to go from 1 down to 201. And you'll see why I do this in a minute. I'm going to initialize another variable that I'm going to call area. So I'm going to do that at this point. So for each row that I come to in this matrix, this is like a spanwise position along your wing. So on row 1, you could think of this as kind of a cut through a spanwise coordinate or a fixed y coordinate along your wing. And I'm now going to loop in the chordwise direction, which is the B size. And now this, I guess, is the tricky bit, because we need to, at this point, we need to ask ourselves the question, well, at this point, are we, remember this is just a rectangular matrix, and within it is your wing. So we're going to ask the question, well, are we at this point on the wing, which is what we're actually asking is there actually a number at this point in matrix C? And we can use the function is NaN, which is, we'll look at the number that's at that point in the matrix, and say is what's there NaN or not a number. So I'm going to go C, and this is the, so IY is the row, IX is the column. So I can say, so if at that point in matrix C you've got NaN, this function is nan will give us a 1. So I want to do something if there's actually a number there that is not NaN. So I'm going to say if is nan of that point in matrix C is 0, then I'm going to do something. And what I'm going to do is say, now at this spanwise position, I'm going to add up the total lift value. Now, of course, the lift is the delta pressure across the wing, which is contained in C, multiplied by the size of the panel at that point. Now, you can go back into matrices X and Y to find out how big they are, and just by looking at the distance between each point in the X direction is 0.01, and the distance between each point in the Y direction, well, is also 0.01. So the size of each panel is going to be 0.01 times 0.01. So as I scroll across this matrix here, as soon as I get to a point in here where there's actually a number, it's not NaN, what I'm going to do is basically add up the delta P values at this point on the wing and multiply them by the size of the panel they represent. And of course delta P times area gives us a force. But what I'm also going to do, and this is why I initialized that area variable at 0 at the start of this loop, is keep track on how big each kind of chordwise strip that I'm adding up or integrating across is equal to. So I'm going to do that at this point. I'm going to end the if statement, end the loop in the X direction, the chordwise direction. And then what I'm going to do is convert that total lift force into essentially an average pressure. So I'm going to take the lift value at that station and divide it by the total area of that chordwise strip that I've integrated across, which has been added up in the area variable here. And then I'm going to end. And if I've coded that correctly without any bugs, that should run. And now I've got a new variable called lift, which basically should have 201 values in it. And I can double check to see if that's correct. Yes, it does, 201. Now some of them are NaN, because at these points, at these Y locations, the wing didn't exist at these points. So this is effectively the root of the wing, and then going out towards the tip of the wing down here. So what I'm going to do is create a little figure over there, and now I'm going to plot. What I need to know is the variation of the Y coordinate. If I check in here, remember the Y coordinate captured down here. So I can pick any of these columns to plot against. So I'm going to plot y column 1 and plot lift, and I get this. Now, first thing you'll notice is, yes, it's a little bit jagged. The reason for that is that the mesh I used to run this simulation on was so coarse, I used so few panels, that there are lots of numerical errors in this solution. The more panels you run, the less you'll get this numerical effect. But we're getting the kind of shape you would expect for a spanwise lift distribution. In fact, what I'm plotting here is technically a spanwise pressure distribution, not lift distribution. To turn these into the lift per unit length or per unit span distribution, you don't need to multiply these by the length of the chord of each of the sections that you've studied. But hopefully you get the idea. And we can kind of sanity check that we're getting the right sort of numbers by going back to that plot. And the delta P's, yeah, they're in the region kind of 200 up to 380. And what we see here is the average pressures as you move in the spanwise direction vary like this. And you can see it's not massively dissimilar to that elliptic lift distribution that we've talked about in lectures.